Previously, we have discussed how to train an encoder-decoder model with input and output sequences that have variable lengths. We now discuss how to use the encoder-decoder to predict sequences of variable length. The first approach is greedy search. For any time step t prime of the output sequence, we search for the word with the highest conditional probability. So what we would do is that we search for the word in the dictionary to find the one with the highest conditional probability, and then keep continuing that way until we get the EOS symbol, end of sequence symbol, or until the output sequence reach the maximum length. Now previously we get this, which is the conditional probability of generating an output sequence based on the input sequence. So what we do is that we take the output sequence with the highest conditional probability. However, there is no guarantee that the optimal sequence will be obtained. Let's look at an example. Let's say we have four words A, B, C, and end of sequence in the dictionary, and more exactly in the output dictionary. We have four time steps. At time step 1, we have 0.5, which is the conditional probability of generating the word A. At time step 2, we have 0.4 as the conditional probability of generating the word B. And at time step 3, we have 0.4 as the probability of generating the word C. And eventually we have 0.6 as the conditional probability of generating end of sequence. At each time step, greedy search selects the word with the highest conditional probability. So then eventually we have the output sequence A, B, C, and EOS. The conditional probability of generating the sequence A, B, C, and EOS is this. We multiply the probabilities together, and what we have is this. Now take a look at another example. Let's say in the second time step, we select letter C, which is the second highest conditional probability. The highest is 0.4 and the second highest is 0.3. In the time step 3, we select letter B, which has the conditional probability of 0.6, and eventually in the last time step we select EOS, which has 0.6 as the conditional probability. Now we multiply them all together. Then the conditional probability of generating this sequence A, C, B, and EOS is actually greater than the previous probability that we got using the greedy search, right? So we can see and we can compare. So this sequence is more optimal. So what we say here is that the output sequence A, B, C, and EOS obtained by the greedy search is not an optimal sequence. Now let's have a look at the complexity. Let's say the size of the output dictionary is 10,000 for 10,000 words, and then the maximum length of the output sequence equal to 10. Then the computation overhead is order of the size of the output dictionary times the maximum length of the output sequence. Think about this like you have 10 time step, right? 1, 2, and 3, etc. up to 10. And in each time step, you look up the dictionary of the size 10,000 words. Right? Each time step, you look up the dictionary of 10,000 words. So then eventually the computation overhead is 10,000 times 10, which is 10 to the power of 5. Knowing some drawback of the greedy search, what can you do differently? One of the ways is to consider the exhaustive search. This approach examines all the possible output sequences and then outputs the sequence with the highest conditional probability. This approach is, however, very expensive. Using the same example, we could see that for each possibility at time step t, we have 10,000 possibilities in time step t plus 1. So then the computation overhead is 10,000 to the 10, which is 10 to the 40, which is very, very expensive. The beam search approach comes to help. This approach is based on the greedy search. There is a hyperparameter that recorded the beam size, and let's say the beam size is k. The maximum length of the output sequence is 3. In this example, k is equal to 2. For each time step, we select k output sequences with the highest conditional probability. At time step 1, we get A and C. At time step 2, we get AB and CE. Eventually, at time step 3, we have ABD and CED. So eventually, we have the set of final candidate output sequences with these 6 sequences. Now, in the set of final candidate output sequences, we take the sequence with the highest score as the output sequence. L here is the length of the final candidate sequence, and alpha usually is selected as 0.75. L to the alpha in the denominator is a penalty on the logarithmic addition score for longer sequences. And as we have known previously, the left side can be extended